We have looked at how to set up nodal analysis equations. We write down Kirchhoff's current law equations at n-1 nodes of the circuit, and in each term of the equation we use voltages which are referred to the reference node of the circuit and element relationships from the resistors in the circuit. Okay, and also we saw how to put it in matrix form. Okay. For this particular circuit, we have got the nodal analysis equation to be times V1, V2, V3, where this is the reference node and these three nodes have V1, V2, V3 with respect to the reference node, equals the source vector I1, 0 and I3. Okay, and of course this can be written as the conductance matrix G times the vector of node voltages V equals the vector of independent sources I. Okay, so this is the nodal analysis equation setup, and of course we can solve for V by using matrix inversion, with which you are all familiar, G inverse times I. Basically, this is saying that we have three simultaneous linear equations in three variables V1, V2, V3, and we solve for it. Okay, when we solve for it, we are basically doing matrix inversion. Now we will briefly look at techniques for matrix inversion later, that is only for hand analysis, right? Things that you already know. The important part is setting up of the equations. Okay, there are many techniques for matrix inversion, and especially for large circuits, a lot of work has been done to figure out efficient ways of inverting matrices on the computer. So the important part for us now is to understand the structure of the G matrix and be able to set up the equations for circuits of any size. Of course, for circuits of small sizes, such as ones with maybe 3 or 4 nodes, you should be able to invert the matrix by hand and solve the circuit. Okay, let's look at the structure of this conductance matrix. First, let's focus on the diagonal elements of the matrix. Okay, what do you see? Let me remind you that the first row is for node 1 and the first column here corresponds to whatever is multiplying V1. Okay, if you look at the element A11 of the matrix, where I use the standard notation, Aij corresponds to ith row and jth column. Okay, we have G11 plus G12. Okay, similarly, if you look at A22, that is second row and second column, we have G12 plus G22 plus G23, and finally A33 is G23 plus G33. You will easily notice that the diagonal elements are basically sum of conductances connected to particular nodes. The first row corresponds to node 1 and the diagonal element in that, element A11, is basically the total conductance connected to node 1. Okay, so this is node 1. We have two resistances R11 and R12 connected to it. So the total conductance would be the conductance of this G11 plus the conductance of that G12. Okay, and similarly, if you look at node 2, there are three resistors connected, G12, G23 and G22. So all of them are summed up and appear as diagonal element in the second row. And finally, node 3 has G23 and G33 connected to it, and the sum of that appears over there. Okay, so the diagonal elements if you look at AII, that is diagonal element in the ith row, then this has the total conductance at node I. Okay, so that should be pretty obvious. Now if you look at the off diagonal elements, this is element A12. Okay, so if you look at element A12, what is that? We have node 1 over here and node 2 over there. Okay, and we have a resistance R12 connected between them. The conductance of that is G12. So basically the element A12 of the matrix is nothing but the negative of the conductance connected between node 1 and node 2. Okay, so you can go through the remaining entries of the matrix and easily verify that that's the case. For instance, the element A23 is the negative of conductance connected between nodes 2 and 3. Okay, and there is a reason for it, which is pretty obvious also. When you write Kirchhoff's current law equation here and look at the term for the current through this resistance R23, what do we have? We are writing currents flowing away from this node. So currents flowing away from this node through R23 would be V2 minus V3 times G23. Okay, so obviously we will have V2 times G23 that appears in the diagonal, and then minus V3 times G23, and this happens for every node. Okay, so if you look at any off diagonal term, it will have basically negative of the conductance connected to that node. Okay, and that's exactly what we have. And also another thing that you observe is that the matrix is symmetric. Clearly we have minus G12 over here and minus G12 there, minus G23 there and minus G23, and similarly 0 and 0. This 0 is because there is no conductance directly connected between node 1 and node 3. Okay, so there is 0 conductance connected between them. Now it's also obvious why it is symmetric, because this is element A12, which should have negative of conductance between nodes 1 and 2, and this is element A21, which should have the negative of conductance between node 2 and 1, which is exactly the same as the conductance between nodes 1 and 2. Okay, so the matrix is symmetric as well. Okay, so just to summarize the structure of the conductance matrix, firstly we will have the diagonal terms AII to be the sum of conductances connected to node I, right? And it's quite clear why this happens, because again we are summing all of the currents flowing out of, let's say, node 2. Now there are 3 currents here through G12, through G22 and through G23. All of them will have V2 in them. The current through G12 is V2 minus V1 times G12. Current through V22 is V2 minus 0 times G22, and current through G23 is V2 minus V3 times G23. So all of them will have V2. So the sum of all conductances connected to a node will appear in the diagonal. And of course the matrix itself is symmetric, and the terms Aij or Aj, which will be equal to each other, corresponds to the negative of conductance connected between nodes I and J. Okay, so this is the structure of the conductance matrix. Let me also add that for an n node circuit, the conductance matrix will be n minus 1 times n minus 1. It's a square matrix. Okay, and also these properties we have written, they are for the specific kind of circuits we have been considering, which consists of only resistances or conductances and current sources. As we add more elements, we see that some of these properties may be modified. Okay, so we will look at those things later. This structure will be obvious when we consider examples of what happens when we make some changes to the circuit. Okay, so that's the structure of the conductance matrix for a circuit consisting of only resistors and current sources. This will become clearer when I take an example, a circuit, and then modify it in certain ways and see how the conductance matrix changes. Okay.